going down. So what I'm doing is this is a loop that's going like this, and I'm now taking the central axis at a certain distance away from the central axis of the loop. We did the same thing for electric field. We found the electric field of that thing. So this is also a doable integral. So the dl is this way, and the r hat is that way. You have to think in 3D here. Okay, you can't do this is 3D. The dl is kind of coming out at you. To make it simpler, you could also view it this way. Imagine looking at this right edge on, so that you only see the edge. Okay, and the current is coming down. Actually, it's coming out at you here, and then it's going into the board right here. So it's the only way I could show this is like, sure, it's coming out at you here, and then going into the board right here. So look at it edge on like that, coming down and then going down, and then you want to find the B field here. Over here, we can actually use symmetry here. Look what's going to happen. The dl is out of the board, the r hat is in, right? So the dl is the vector coming out of the board. The dl here is going into the board, and the r hat is this way. Okay? So when I do the cross product of that, as far as direction-wise, what happens? Okay? This one, dl, crossing the r hat, gives you like that. Okay? This one gives you a B field here that's this direction. Okay, so let's do that again, like that. And then I got to tilt my palm because the r hat is pointing down. So it gives you like that. This one gives you like this. You got to tilt your palm up like that. So it creates a dB that's this way. And now I'll be able to use symmetry. I'll argue that the y component of that cancels. Only the x component survives. dB total is equal to 2 dBx, which is 2 dB cosine of theta. Right? So dB total is going to equal 2 times cosine theta times dB is going to be the mu 0 I over 4 pi. The dB is mu 0 I over 4 pi r hat crossed into dl over r squared. So that's the dB. But now I got to take a cosine, twice the cosine of that. Okay? And then you get mu 0 I over 4 pi. R hat crossed into dl is going to be dl times what? Sine of this angle. No, actually, sorry, no. I made a little mistake here. The dl is actually coming out of the board, right? And the r hat is this way. What's the angle between them? It's 90. You got to think three-dimensional here, right? The dl is not coming down. It's going out of the board and then into the board. So I'm analyzing this dl and then this dl. So this is out of the board dl, and then the r hat is this way. So they're in two different planes that are perpendicular to each other. So sine of the angle is 90. Same here. So the cross product of these two just gives you dl and then sine of 90. And then now we could put in here mu 0 I over 4 pi r squared is this r, which is x, and then this is the radius. So r squared is equal to x squared plus the radius squared. And then what's left? Cosine of the theta. What's cosine of theta? Theta is this, which is the same as this theta. So cosine of theta is x divided by one of the r's, right? X over r. So cosine of theta is x over r, which makes this a what? A 3/2, right? Because I already had x squared plus r squared, because it was r squared, the little r squared, and then now I have another r, so you have 3/2, and then what's left? Well, the dl is left. Now I integrate this. Now it looks like a complex integral, right? Well, how am I going to integrate this? But it's actually a very simple integral, because it's really not even an integral, right? If you really think about it, for every element along this circle, for every element, dl, the x and the r don't change, right? The x and the r don't change. This one come out, this one go this way, this one come this down. The x is still this, and the r is still that, okay? And so it doesn't matter where the element is, the x and the r are just constants. They're not integrate. You don't have to integrate them. Okay, as a matter of fact, it would be wrong if you integrate them. So none of this is part of the integral. You just got to integrate the dl. Okay. So B total is therefore going to be just all of this times the integral of just the dl over the whole circle or half the circle. Okay, notice here I used the symmetry to argue that the total B is going to be twice the B of each one, twice the x component, because I argued that this one is going to cancel with this one. That means every element that has, let's say this one, has a counter element here. This one cancels with that one. The y component cancel. So when I'm integrating, I should only integrate over half the circle, because I've already used the symmetry. So I should only integrate this over half a circle, which will become pi r. So the final answer, this will become pi r. So the pi and the pi will cancel. So I'll get mu 0 I x r over 4 times x squared plus r squared to the 3/2. This is the magnetic field of a whole wire at a certain distance x from its central axis. Okay, if we did the process correctly, okay, if we did the process correctly, what should the magnetic field come out when I put x equals 0? Limit as x goes to 0. So as I go to the center of the coil, what should the magnetic field of the center of the coil be? Well, we just did the answer in example 2. The magnetic field of the center of a coil should be mu 0 I over 2r.